Alright. So I sent out a homework over the weekend with normal random variables. We didn't talk about everything, so I figured let's go ahead and go through some more examples. And then at some point, mid-class, we're going to switch over and start talking about chapter 4. Chapter 4 will be a quick chapter because we've talked about we've talked about a good portion of it. So, expected value and variance. So last time we had seen that if I have normal random variables and I keep, on the homework I didn't say it, so I don't say it, still, if I'm taking multiple copies of the same random variable, assume independence unless I say otherwise. That's sort of our standard will be independence unless otherwise stated. Right. And so what we did last time is we talked about how random variables add together, and we saw that if x is normal with mu1 sigma 1 squared, and y is, or well, x1, and x2 is normal with mu2 and sigma 2 squared as its two parameters, and everything is nice and independent, then x1 plus x2 is what? Well, the easy part of that is normal, right? Or normal. But what are the two parameters?
mu1 plus mu2.
Yeah, mu1 plus mu2 and
Sigma 1 squared.
Sigma 1 squared plus sigma 2 squared. This makes life so much easier, even if it wasn't just because we have to end up using a table to look things up. But when I compute a probability attached to something like this, remember I have to do a double integral over some region in the plane. And what this is allowing me to do is to think about this as a new random variable without having to come up with my double random variable, because I know what sort of random variable this is going to be. It's going to be normal, and I can figure out what the parameters are supposed to be. Okay. So we have that result, and I guess the other thing we have is that sort of comes off of this is if I get a new random variable y, which is going to be a x1 plus b. This is an old result, but y will be a normal random variable with, what are the parameters going to be? I'm just changing it, constant times x1, that one up there, plus another constant. A mu1 plus b, and then what's the sigma squared? A squared sigma 1 squared. Okay. Or A times sigma squared. Yes. So if I do a linear combination, right, if I have a scalar times a normal random variable plus some other scalar, how does it change my mu's? Well, my mu will be a mu1 plus b, and my sigma squared would be a squared sigma squared. Which, one more step here, we might as well get it all out and then and go from there. If I have an a x1 plus b x2 plus c, so now I'm going to start taking linear combinations of my two random variables. And again, I know they're both these normal random variables with mu1 and mu2, sigma 1 squared and sigma 2 squared, right, as the appropriate variables. Right? Anytime I take a linear combination of two normal random variables, I get another normal random variable, Now the question is just, what are the parameters? So any guesses as to the mu parameter here? Yeah?
A mu1 plus B mu2 plus C.
Plus B mu2 plus C, yeah. Essentially, we're just plugging our mu1s and mu2s into this formula in that way. And we'll see another reason why in the not too distant future, but yeah, that's how they combine. And then how do the, what's our sigma squared gonna be for this normal random variable?
A squared, B squared, sigma squared.
A squared sigma 1 squared, right? Because A is attached to the sigma 1 squared, but we get a square when we do that. The B is attached to, so B squared sigma 2 squared. And what do we do with the C? C just shifts things to the right and left. It doesn't spread, it doesn't change the spread. Yeah. So it changes by A squared sigma 1 squared plus B squared sigma 2 squared. So if I want to start taking linear combinations, which I do, taking linear combinations to borrow some language from linear algebra, I can certainly do that, and I still get a normal random variable because of these two results that we have right here. And then it just tells me, okay, which normal random variable, what parameters am I going to use? That's why, by the way, when we now take, say, we looked at this last time, I'm not going to do this again, but x1 plus x2 plus x3. So here's the situation where we had our bags of carrots. We said the weight of the bags of carrots was approximately normally distributed. This is its mu, this is its sigma squared, and I'm going to add 3 copies of that together, right? So I'm going to average the weight, or not average, but I'm going to take the total weight when I take 3 bags of carrots together. And that's going to be normally distributed, and then I just have, because it started out normally distributed, and then what is the mu going to be?
3 times 1.8.
Yep, just this plus this plus this, which is 3 times that. And what is the sigma squared going to be?
3 times 0.07 squared.
Yep, this plus this plus this, which is just 3 times 0.07 squared. So we did that last time, and so any probability or any probability question I want to attach to this sort of random variable, I certainly could if I wanted, and I think we finished off the last step like this. Right? Now I know this is a normal random variable, and I can switch it back to standard normal if I want to compute this probability or probability like that. Okay. I'll do a slightly different one here. Here's a new random variable d, which is going to be x1 minus x2. And so if I'm dealing with a random variable like this, x1 is just the first bag, right? The weight of the first bag, and x2 will just be the weight of the second bag. And my new random variable is doing what now? I'm going to take 2 bags of carrots, I'm going to weigh the first bag, I'm going to weigh the second bag, I'm going to subtract those weights, and that's my random variable. And I'm going to answer this question, what is the probability, this is one off of the homework, what is the probability d, right, let me just write it this way, x1 minus x2 is between 0.1 and negative 0.1. What is the probability if I pick up 2 bags of these carrots and I weigh them, their weight is less than 1/10 of a pound? Okay. Well, this is what sort of random variable? It's a normal random variable. Right? I mean, this is just a linear combination. it's 1x1 and negative 1x2s. So what are the parameters? So I'm going to take one of these, and I'm going to do what? What will the mu be in this particular case? Yeah. It's one of these plus negative one of these, or one of these minus one of these. Okay. I'm just going to write 1.18 minus 1.18. Essentially, that's what this is telling me, is just plug in the particular mu that goes along with it in place of your random variable, and there's no constant term there. Okay. So that's 0. What about the sigma squared? Well, from the x1, it will be 0.07 squared, right? But then what am I going to do? You add negative 1 squared of the other 0.07, right? Because squared, right? Because we could think about this as plus negative x2 squared, right? And so then we have this. And so then we can see what it'll be a squared, there's a 1 in front of the x1, sigma 1 squared, plus b squared, there's a negative 1 in front of the x2, so I'm going to take that and I'm going to square it, and I'm going to multiply it by the sigma 2 squared. So yes, I just add the two things together. So this would be 2 times 0.07 squared. Yes, the sigmas never subtract. They never subtract because we're going to take whatever coefficient is in front of them and we're going to square it, which is going to make it a positive. So now if I want to figure out what's the probability that the difference in the weight is between negative 0.1 and 0.1, it is worth noting how we would have done this, how we would have calculated this back in chapter 3, right? x1, x2 are my two random variables. x1 minus x2 would be some line that would go, right? Actually, the inequality would give me these pair of lines at a certain distance apart, right? And I'm interested in the region between those two lines, right? And so then I'd have to set up my double integral, right? This is the chapter 3 way of doing problems like this in general. Set up my double integral, integrate over this region, right? Certainly could do that, and go from there. Now, obviously that's not particularly nice because our probability density function doesn't really allow me to do a lot of double integrals. But the other nice thing here is I'm actually not going to have to do any double integrals to solve for this because I understand now from our earlier results that when I subtract these two random variables, I get another normal random variable, and then I can take my normal random variable and I can switch it back to a standard normal random variable. Okay. I could get z-scores for my two endpoints. Right? How do I do that? I subtract off the mean, and I subtract off the mu, and I divide by the sigma. Right? So I have this negative 0.1 minus 0 divided by, what would I end up dividing by?
2.0 times 0.7.
Yeah, root 2 times 0.07, right? Which would be my new sigma for this random variable. Right? And I'm subtracting off 0 and I'm dividing by my sigma here, right? That's what gives me my z. And then over on this side, I'll take my 0.1 minus the mean that I calculated and divide it by the, again, root 2, the square root of this thing, which is root 2 times 0.07. And then I go ahead and calculate those things. Looks like, let's see, 0.1 divided by root 2 times multiplied by 0.07 is 1.01, okay. So it looks something like probability that Z is between 1.010 and negative 1.010. Which would be, remember this is sometimes used as the cumulative distribution function for the standard normal for Z, for standard normal random variable. So I plug that into plug 1.010 into that minus, and then I'll plug the other endpoint right into that cumulative distribution function. And then I go ahead and pick up my handy dandy standard normal random variable estimator, unless I want to fire a R there. But I can do this, right? I can plug in, I can look at 1.01, I guess is what it goes out to, on the outside, 1.0 and go over to 1, and I get 0.84375. Right? Gives me the probability to the left of that 1.01 on the standard normal random variable. Okay. And the one that I put on Blackboard actually has positive and negative values there. We don't necessarily need them because the standard normal random variable is symmetric about the origin. So this number, this is saying basically 84.375% of the area is to the left of this number, okay, which would mean 1 minus it would be to the right of this. But of course, 1 minus that would be the area to the left of this one with the negative value there. Okay. But I'm lazy, I'm just going to go ahead and look it up. Negative 1.010 is, and that gives me 0.15625. And you can check that this number is 1 minus that number because our cumulative distribution function and our probability density function are symmetric about the origin. And then that would give us something like a, what is that, 0.6 and a 9, I think it's 75 if I remember correctly.
0.6875.
0.6875, thanks. 875. About 69% of the time, I would expect that I pick up these two bags of carrots and the weight would be within a tenth of a percent, or a tenth of a pound of each other. Right, that's what we're saying. And again, this is a much nicer way of doing this because our normal random variables combine in this nice way to give us new normal random variables. I don't have to, even with these multiple random variables, I don't have to set up this region of integration. I don't have to perform the double integral. I just have to figure out which normal random variable is it, what are the two parameters, and then I'll take that, set up my question in a probabilistic way, adjust it to the standard normal by finding those z-scores, right, and then looking values up on the table. Let's see. One other one that's probably worth talking about a little bit is, I'm trying to think here. Here's one where, the same one, talk a little bit about X bar. And suppose X bar is, let's take our bags of carrots. And of course, X is, I'm going to pick up one bag of carrot and I'm going to weigh it. And then that's telling me the probability density, or that's telling me the random variable that's associated by it. It's normal with those two parameters. Okay. So now X bar would be something along the lines of, I'm going to take 10 bags of carrots. Maybe I'm part of quality control or something like that. And I'm going to take 10 bags of carrots, I'm going to add them together. Of course, all of this, I'm still assuming these carrots are independent. I'm going to assume that somebody didn't take all the big bags of carrots and set them aside, right? So I have these bags of carrots, and I'm going to take 10 bags of carrots that are all normally distributed, and I'm going to add up their weights and divide by 10. Right? I'm going to figure out their average weight of 10 bags. Now, my claim is X bar is a normal random variable, and we just have to figure out what the parameters are. Because, for instance, when I go ahead and add 10 copies of these things together, I'm just going to look at the numerator for a second. I do know when I add together those 10 copies in the numerator, I do get a normal random variable. And what are the parameters there? The mu would be, actually 10's a nice number, we can just look up there and say, what is it going to be? You can do the arithmetic in your head, right?
11.8.
What's that?
11.8.
11.8, right? It'd be 10 times the mean up there. The standard deviation would be 10 times 0.07 squared. I'll just do it, right? But it'd be 10 times the mean and 10 times the standard deviation. Again, I'm assuming independence in all of these things. Okay? That's what I would get if I were just to take this random variable that's part of the numerator. But now what am I going to do? I'm not going to use this random variable. I'm going to take this random variable and I'm going to put a 1/10 out in front of it. What's that going to do to my random? Well, I know that if that's really this case where b is equal to 0. I know that if I take a normal random variable and I multiply it by some number, I get another normal random variable. So if I take this normal random variable and I multiply it by 1/10, my mu will be 1.18, 1/10 of this, right, which would be 1.18. Hopefully that makes sense. If we believe that this mu is telling me my expected value is telling me, I keep using the word mean, what I expect to happen, right, the average, then if I average 10 of these things, I expect it to be the same. I expect everything to be centered around the same point, which it certainly is. What would be the sigma squared in this case?
Maybe 0.1.
What's that?
Maybe 0.1, because you have to square the 10, so it'd be 10 over 100.
Yes. So I would take this 1/10 and I would square it, and then I'd multiply it by 10 times this 0.07 squared. Yes, but the point being here that this constant out in front, for the sigma part of it gets squared. So I actually get a 10 squared in the denominator, which will cancel out with one of the 10s, but it'll give me a 0.07 squared divided by, divided by 10. And notice, when I just dealt with one bag, I get the same mu, but my sigma squared is larger here than it is over here, right? Actually larger by a factor of 10, or I can say it's smaller over here by a factor of 10. So we could ask a question, let's put a question. So I gave a couple of questions that look like this off of the homework. Find the 90%, and in statistics we would call this a confidence interval, but let's just call it a probability interval. For x, and then we'll do it for x squared, right? And so what do I mean by this 90% probability interval? It means that I'm going to find these 2 points on either side of x. We're going to use x first, and then we'll do it for x bar. Where I have some a over here and some b over here, where 90% of the probability is on that interval, is on that region. And not just any 2 points. Typically we would pick the 0.05 quantile over here, so 5% of the probability would be outside of it to the left, and we'd pick the 0.95 quantile over here, which means 5% of the probability is on the right. So it's really the middle, we could think of it, 90% probability. Right? And so I want to find this interval in this way. And it's not too bad. So this is my original x. To find, I don't remember if we did one of these last time, but we can certainly do one of these pretty easily. To find q sub 0.95, we're really just looking for the number that gives me a probability 0.95 to the left of that. That's what the 0.95 quantile means. That's what the 95th percentile means. It means 95% of the probabilities to the left, or 0.95 of the probabilities to the left. And then I could go ahead and answer that question by making this a standard. I always go back to standard normal random variable, right? By subtracting off the mean and dividing by the sigma, right? So I have this q of 9.95 minus the 1.18 divided by the 0.07, and I want that to be 0.95. And again, I'm going to work with this one first. I want to compare my answer here to what I would get if I asked the same question over here. So I set this thing up, I want to find this quantile, so I subtract off the mean, I divide by the sigma, and I know that this value should be the 95th quantile for the standard normal random variable. And then I go to my nice little table here, and I figure out, okay, which number would give me a 0.95 probability. So now I look in the middle of the table, alongside here, in the middle of the table for 0.95, and I see a 0.94950 and a 0.95053. The 0.949, right? Yeah, that one's one of them's a little bit closer than the other one, and that would be 0.164, right? So I have 1.6 over here, and then if I go up to 4, that's the point that gets me to the closest to the value that's going to give me an area to the left of that being 0.95. Okay. Look that up, number right there, up the standard normal random variable. On this homework, I asked a whole bunch of these middle 90%, right? And so I asked for the 0.05 and the 0.95 quantile. Actually, more often than not, it seems like we're interested in 0.025 quantile and the 0.975 quantile. Because how much probability would be between those two? 95%. And just in general, if you're trying to include the things that you consider likely, it seems like more often than not, you'll take a middle 95%, what's called a confidence interval. Because how often does something happen? How often does something not happen if on a 95% confidence interval? Well, 1 out of 20, right? And 1 out of 20 isn't a frequent thing to happen. But how much ends up outside of this? 1 out of 10? 1 out of 10 doesn't happen a lot, but we're not shocked if 1 out of 10 happens. We're a little more surprised if 1 out of 20 happens. So oftentimes, the quantiles we're interested in are what's called the 0.025 and the 0.975, because we're interested in a 95%, but 90 perfectly good one also. Okay. So here, then the actual number that I'm looking for my carrots, my Q of 0.95, right, should be a number such that this thing here is equal to 1.64, this value here I looked up off the table. So I just want to solve for this, so I'm going to multiply both sides by this sigma, and I'm going to add my mu to both sides, and it's going to look something like 1.18 plus this 1.64 times 0.07. Okay. And whatever that number is, that would be the 95th quantile for this random variable. That would be the value for which 95% of the bags of carrots are less than that. And a nice thing to point out here is when it comes time to find the 0.05 quantile, I can certainly take advantage of symmetry, because if 95% of the probability is to the left of this point, that means 5% of the probability is to the right of this point. And the fact that everything is symmetric means that what number would I plug in here to have 5% to the left of, 5% of the probability to the left of the point? Right? My 1.64 could just become negative 1.64, right? If 5% of the probability is to the right of 1.64, 5% of the probability is to the left of negative 1.64. Right? Again, it has to do with the symmetry of the standard normal of our standard normal random variable. So for this one, the only thing that changes is that's going to end up being a negative value, and I get a 1.18 plus negative 1.64 times 0.07. Notice that would give me an interval that, we could calculate these numbers, but I don't feel like pulling the calculator out. It's not that important, the actual numbers. But notice it's going to be about, it's all centered around the point 1.18, right? Around the weight 1.18. And it's, 1.64 times this standard deviation. If I stay within that region, my claim is 90% of my bags of carrots would stay within that region. Now, what if I were to do that for this example? Okay. Let's do the same thing for x bar. Find this middle 90% probability interval for x bar, which is really just asking that same question. Now, what value could I plug in here so that x bar is between those two values, right? My q's will be different numbers this time because I have a different random variable. Every random variable I have would give me different values. But I want that to be 0.9, and in particular, I want x bar less than q of 0.95, right? Same argument as before. Now, how am I going to figure out this number this time? Well, my x bar is what kind of random variable? Normal. So I'm going to switch it back to standard normal by subtracting off the mean and dividing by the sigma. What is the sigma in this case?
0.7 over square root.
Yeah. It's the square root of this number instead of the square root of the far one, right? So it would be 0.07 divided by root 10. Equals 0.95. And other than that, other than this sigma's different, there's nothing else that's different in this problem. That this number here will be 1.64, right? Because from the standard normal random variable, 1.64 is that number where 95% of the probability is to the left of it. And then if I want to figure out what the Q point, right, the 95th quantile is in this case, I'll just multiply, let's see, this is equal to that. So I'll multiply both sides by my sigma to get it up here with this thing. I'll add my mu to both sides, and I'll get something like a 1.18 plus 0.7 over the square root of 10 times, oops, I was writing it the other way around, I'll write it. 1.64 times, let's see, 0.07 over the square root of 10. And for the 0.05, right, it would be the same thing with negative 1.64. 0.07 divided by root 10. So if I wanna know where 90% of my results from this experiment, okay, this is a different experiment, this is where I take 10 bags and I average their weight. Right? So I add all the weights up and I divide by 10. Okay. How has this interval on which the likely things, the 90% of things happen, how has it changed from here to here? Are they both still centered around the same point? Yes, this 1.18, right, the mu's did not change. Okay. But how did the width of the interval change? Which one's bigger? Yeah, for x, right, we got this interval that was centered around 1.18, and there are these two numbers, I think probably one of them's something like, does someone have one of them, 1.27-ish, I'm guessing, but, yeah, it's 2.26 or something like that, but there's this interval for the x's where 90% of all of the outcomes end up on that interval, which means 10% end up outside of that. How big would this interval be for x bar now?
So the 90 percentile interval for x is 1.07 to 1.29, and the 90% interval for x bar is 1.14 to 1.22.
1.14 to 1.22. And right, this is a smaller interval, right? By how much? Well, the square root of 10 is a little bigger than 3, so it's about a third the length of it. And what's that saying? It's saying that the things that are most likely to happen are going to be much closer to 1.18 than they would have been in the x case. Why? Well, because I'm averaging a bunch of things. And does it make sense if I average a bunch of things that it would work its way out? Yeah, because I have a normal random variable. Right? I have this normal random variable, and lots of things could happen. Anytime I weigh one of them, right, I could end up with that. I probably get one of those, right, some of those, but I should get more things here in the middle where things are high. But if I weigh 10 things, I don't expect all 10 of them to be sort of bunched over here on the right-hand side. I don't expect that to happen. That every time I get something a little big, I kind of expect that sooner or later I'll get something on the other side that will balance it out. So that when we end up averaging those things, everything gets clustered when we average a little bit more tightly, or actually maybe even significantly more tightly than it would otherwise. So if we wanted to know whether or not our bags of carrots are fitting some sort of specs that we're looking at, if we average a number of them together, right? Now all of a sudden, if I average 10 of these things together, I have a pretty tight, at least reasonably tight interval on which I expect those outcomes. And if they fit outside of those outcomes, maybe I call them abnormal and I think there's something wrong with my process. Maybe it doesn't pass my quality control and my quality assurance. Okay? Whereas if I just pick up a bag at random and weigh it, there's a pretty big interval on which these things could fit, and I could end up on the outside of those things much more easily than I could when I average a number of things. I'll just leave it at that. So when we take a bigger sample and we average things, it does tighten things up. This is why places like 538 will take a bunch of polls and they'll average those polls for the same reason, because the things that are a little big and the things that are a little small should all cancel out. Now, the important thing there is, of course, assuming that these numbers here sort of are representative of what we want, okay? And if they're off, right, that's what we call bias. Right? Maybe we forgot to hit the tare button on to reset our scale, and everything ended up, 0.05 off in terms of weight. That certainly could happen. Those would be called biased measurements in that case. But as long as everything's calibrated correctly, we sort of expect this to happen. And then if I average a number of things, everything's still centered around the same point, but it should keep everything a little bit tighter. How much tighter? Well, square root of 10 tighter. some sense, dividing by the square root of 10 tighter. Okay. We took a sample of size 100, my square root of 10 would be a square root of 100, which would be 10, right? It would make it even tighter yet. If I were to take a sample size of 1,000, right, which is what most poles are, then it would make it tighter yet, and we could start being a little bit more confident in the sorts of things we work. Okay. All right, one more, let's see, one more. I think this is here's a random variable. This went out for the homework also. These numbers aren't exact, but they're decent approximations. The height of men in the United States, adult men in the United States, is approximately normally distributed with mean equal to 70, this is in inches, and sigma squared equal to 4 squared. The height for females is approximately normally distributed with mean equal to 65 inches and sigma squared equal to 3.5 squared. And all this is to point out that we don't have to keep using the same random variable repeated over and over again. Sometimes we want to compare two different normal random variables. And so there's a question that says, something along the lines of, what is the probability that a randomly chosen male is at least 12 inches taller than a randomly chosen female? Which means that we're setting up some sort of probability question that's going to compare the heights of males with the heights of females. In particular, we want the heights of males to be at least 12 inches more than the heights of the female chosen. How would we write that in terms of a probability question with our random variables?
M minus F is greater than 12.
M minus F is greater than 12. And then the question would be how likely is that to occur? Well, M is normal, F is normal, M minus F is normal. Now the question is, what are the parameters? So what would the mu be for M minus F? M minus F would be 70 minus 65, right, which would be 5. I expect the male to be, on average, 5 inches taller than the female. Why? Because the male is on average 70 inches tall and the female is on average 65 inches tall, right? So we just subtract those two things. That's how normal random variables fit together. What about the sigma squared for it? What would be the sigma squared for M minus F?
4 squared plus 3.9.
Yep, 4 squared plus 3.5 squared. And you could write, again, 4 squared plus negative 1 squared 3.5 squared. But we never subtract when it comes to sigmas. We always add because of this, right? Any number, even if it's a negative number in front of our random variable, ends up getting squared, right? Becoming positive, adding to our sigma squared. Right? So we would get that. So to answer this question now, I think I have a number out of that one somewhere here.
It's 5.32 squared.
5.32 squared? So now to answer this question, what's the probability that a randomly chosen male is at least 12 inches taller than a randomly chosen female? I can take M minus F, which is a normal random variable, and convert it back to a Z, right? A standard normal random variable, by subtracting off the mean and dividing by the sigma, right? And so it would be my 12 minus 5 divided by sigma, which is, see why it's nice to write these things sometimes as the sigma squared? Because that's, more often than not, that's what you have to work with. It depends, right? It's nice to have sigma squared there, because then we just add these two things together. But when we actually go to use this for calculations, we divide by sigma, not by sigma squared. So you could say, well, why don't we just have a 4 here, and why don't we have a 3.5 here, and why don't we use those as their parameters? Because that seems like what we're doing for our probability. Well, then I would have a different formula, right? And if I added, if this was my parameter and this was my parameter, then my sigma over here would be 4 squared plus 3.1 squared, the square root of that. So it's nice to deal with variance in probability because we're just adding these sigmas together to get this one. But when we actually go to compute a probability, switch things back to standard normal, we do have to take the square root. Okay. So our compromise oftentimes is just write it as sigma squared. So then we get this, okay, which gives me a z-score of, you have this number, it's been on top of the numbers here.
I got 1.32.
1.32. Okay. And that's probability z is greater than 1.32, which would be 1 minus the phi of 1.32. Right? Phi is telling me the probability to the left, I want to know the probability to the right, so I will take 1 minus that, and if I plug that into my little table over there, it's 1 minus 0.90658, which is approximately 0.09, what is it here?
342.
So this would happen about 9.34% of the time. Okay. Not common, but not incredibly uncommon. Yes?
Could we also do something like find the probability that the average of n differences was greater than something?
For men and women, for instance. So if you wanted to look at, say, the probability m bar minus f bar, so you average 10 men and 10, or what do you?
So average 10 differences. So like m minus f was like random variable, normal random variable, and then find the average of that.
Oh, the average difference. Yeah, so you're saying, could we take m1 minus f1 plus m2 minus f2, is this what you're saying? A certain number of those, and we're adding those together. And what's the probability it's less than, and let's just give a number like 1 inch, something like that, or between -1 and 1, something like that. But actually, what is that? If I have m1 minus f1 plus m2 minus f2, how else could I rewrite that? That is also just my m bar minus my f bar, right? Because that's all my m's minus all my f's. Well, I guess I'm not dividing by, oh, you wanted to average it, so you wanted to divide it by, let's say, 10, if that's what it was. Okay. So it would be the same thing as this. And yeah, absolutely, right? Because we'd probably just take it piece by piece. M bar would be, and we'll have to, this will take us through the end of it, right? So M bar would be, if I took 10 copies of this independent, again, independent, even if I don't say it, I'm talking about independence. If I average 10 copies of M, what's the mu going to be?
70.
70. And what's the sigma squared going to be?
4 squared over 10.
4 squared over 10. Okay. 10 times 4 squared for the sum, divided by 10 squared, right, for the quotient. Yeah. It's going to be 4 squared over n if I want to do any. And that's my normal random variable for m bar. And f bar, the average of 10 females, would look like, 65. And then I have my 3.5 squared divided by 10. Okay. Now, what is it going to be when I take m bar minus f bar? Again, it's going to be a normal random. This is the nice thing about normal random variables is I sum them, I subtract them, I multiply them by constants. I take any linear combination of normal random variables, I always get new normal random variables. It's almost like they're vectors. They're closed under linear combinations. They are vectors, right? They're closed under linear combinations, right? It's a subspace, if we want to think about it that way. And so now, what would which normal random variable? I just have to say which with parameters. So these two individually are these, and then my mu would be 70 minus 65, which would be 5. I do expect the difference to be 5. Now the big question is, what do I do with my sigma squared?
4 squared plus 3.5 squared all over.
Yep. It's this one plus that one, right? Which is, yeah, we could write it as 4 squared plus 3.5 squared divided by 10. And now if you want to compute any probability attached to it, now it's a normal random variable. And the nice thing is, we took this, if we wanted to actually set this thing up, we would have to perform an integration in R20, right, in 20 dimensions. We'd have to set up this 20, not double integral, 20 integral, right? And what we've just done, we've been able, just with these nice results, collapse it all back to a single probability question in one variable, right? Because that's how these things are related. And then I could, and actually I don't even have to do an integration because then I look up at my table, because I convert everything back to standard. I mean, it's a huge deal. I mean, it would be a 20-dimensional integral if we had to do this by hand. And I can't oversell how valuable taking a double integral in R2 is and crashing it down to a one-dimensional thing. Until, I mean, you can't really appreciate it until you start thinking about, what if I had to set up this integral in R20 and figure out the particular limits integration alone would just be annoying. So, all right, so huge results. Summing random variables, great. The big thing and the mystery that we need to unlock throughout the last few weeks here is, why is it that when I add up any other random variable, they all start becoming normal random variables? Because if I take any other random variable that's not normal, I start adding it up, right? Independent copies of itself together, I end up with a normal random variable. Why in the world would that ever happen? But it's what happens. Okay? So next time we'll talk about expectation, expected value. We have talked about the first 2 sections of chapter 4 already. So we'll just quickly go through those. And then we'll go to the other side and start looking at some things with not just expected value and variance, but something called covariance, where I can compare somehow variance between 2 different random variables. Okay, so we will stop.